I learned from the mistakes. This I would consider an optional step. We mentally just rewrote it as an excellent tool. But the power rule, or sorry, chain rule is a half comes down, drop it to the negative 1/2. Inside stays the same. Then times derivative of the inside. What's the derivative of the inside? 0 plus 1 over x. So did you get the first one? Yes? Chain rule? And most importantly, not most importantly, but as important is, did you label? That's the derivative. Okay? Next. The outside is cosine, so the derivative of the outside is negative sine with the inside the same. Then times the derivative of the inside. What's the derivative of 3x squared plus 1? 6x, right? And last but not least, in this case, the outside is to the fourth, so the derivative on the fourth is 4 comes down, drop it to the third, that's the derivative on blank to the fourth. Inside stays the same. Then by chain rule, derivative of the inside times the derivative of the inside. Derivative of 3 root t is 3 over 2 root t, or if you like, you could have this 3 halves t to the negative 1/2, that's fine too, plus 1. How's your chain rule going?
It's great.
Good? Those are good. Okay. I already walked through this here for Loretta and people up front. So the idea on yesterday was if you have a coefficient, you can move it out front and just focus on the integrating the term. The power rule, which you would first want to rewrite that as a power so you could use the power rule. For antiderivatives, you raise the power by 1. So instead of like a derivative dropping the power by 1, we raise the power by 1 and divide by the new. When you integrate, raise the power by 1, divide by the new. Raise the power by 1, divide by the new. So it's 1/20 times u, 3 halves over 3 halves, which could definitely be cleaned up, but I didn't bother, plus c. You follow? All right, now let's talk implicit differentiation, or equations where y isn't solved for. How do you take the derivative? The key idea is chain rule. So when you take the derivative on y cubed, yes, it's the derivative on the outside, 3y squared, but then times the derivative on the inside when you have a y term, and the derivative of the inside is dy dx, yeah?
Yeah.
Plus, this one requires a product rule. So first stays the same, x, times the derivative of y is dy dx, plus second stays the same, y, times the derivative of the first, which is 1, equals derivative of e to the x, e to the x, all right? After that, we want to solve for dy dx, so everything with the dy dx term, we're going to keep on the left side. So I'm going to call it the dy dx's consists of 3y squared plus x, okay? Everything without a dy dx gets moved over, so on the other side I'm going to have e to the x minus y. At the end of the day then, dy dx is e to the x minus y divided by 3y squared plus x. How did we do there? Good. All right, last but not least, differentiating here with respect to time. That is to say that x and y, instead of depending on each other, they actually both depend on time. This is what parametric equations and Calc 2 uses a lot. If I wanted to know where it was over time, something like a whatever, any kind of movement, then you would talk about change with respect to time. So if I take the derivative on 2x with respect to time, it's the derivative of the outside, which is 2 times the derivative of the inside. And what's the derivative of x with respect to t? dx dt. Okay. Then the derivative of negative y squared, which is negative 2y, but then times the derivative of the inside with respect to t. dy dt, right? Equals natural log of x. The derivative of the outside is 1 over x times the derivative of the inside. dx dt. All right, now then, solving for dx dt means I want to get everything with the dx dt on one side. Those guys both have a dx dt. So I'm going to move that one over and leave the dy dt term on the left. And so when I do, I could take out dx dt, and I'd have something like 1 over x minus 2, that quantity times dx dt on the right. Do we agree?
Yes.
All right, therefore, dx dt is negative 2y dy dt over 1 over x minus 2. Pause real quick and notice how I wrote this, okay? I know it feels like dy dt is a fraction and it would be tempting to write it this way. Don't write it that way, okay? This dy dt, it's one thing. You keep it together, okay? So that's why it's written like that, not like I'll have a dy up top and you just don't do that, and you'll see why when we get to related rates. All right, you with me?
Yes.
All right, here we go. Now listen, the book sometimes I feel like it gets the order a little off from what I would do, and so in those cases I'll change it. This is one of those days. Differentiability doesn't actually come till much later in the books at 80 or so, and that's too late. You need differentiability to do critical numbers. So, this, as often is the case, is going to be a little different than what the book does, at least in the order. So make sure you pay attention because your notes are going to be your main source. There are some times when a derivative doesn't exist. In fact, there are 3 times when a derivative doesn't exist. I'd like to introduce you to maybe why that would be the case, or at least one of those would be the case. All right. So imagine if I use the alternate definition of the derivative to find the derivative of f of x equals x minus 2 at x equal 2 and sketch a graph. All right. Let's start with sketching a graph. What does the absolute value of x minus 2 look like? Describe the shape and the placement. Shape is a V. Good job. Good voice over there. That's cool. Okay. And the place is where? Right, left, up, or down? Fulton? What? Up? Very good. Actually, look at the function still. Right, yes. Okay, so right. It's a right V, yes?
Yes.
All right, so it looks like this. Here's 2. Now, this is a good review of the main concept of the derivative. I know it's tempting after learning all these derivative shortcuts to leave the definition of the derivative behind, but that is the concept, and you must always have it in the back of your mind. So the idea then of a derivative, remember, is to take the slope between 2 points and get the points closer and closer together so it approaches the slope at a point, right? That is the idea, yeah?
Yeah.
In the alternate definition, you let one of the points be the point at which you want the derivative, so in this case 2, and then you let x equal any other point on the curve. Then I could find the slope by taking this point then is x, f of x, right? And this point is 2, f of 2. So how could I express the slope between those 2 points? Change of y is f of, that's an x, sorry. F of x minus f of 2 over change in x is, that's the slope right now when the points are separated. How do I get the points close together? Take the limit as what happens? X goes to 2, right? Now, all that's super duper, but keep in mind that when you do a limit, x is supposed to be able to approach 2 from either side. So, in other words, I don't necessarily have to have x being a point on the right. I could have x being a point on the left. Either way, it's supposed to be any other point on the curve and 2. Now this is going to be the key here, is look at how this is different from each side. So imagine that if x is right of 2 case, then the limit as x goes to 2 from x would be approaching 2 from above, yeah? Are you with me? X minus 2 minus, actually, I'm just going to do f of x minus 2. I don't need the actual functions. F of x minus f of 2 over x minus 2. Now, right now, what's the slope here? If x is above, what's the slope between these 2 points? What's the slope of that line? Okay, maybe it's confusing to think slope of a line when it's absolute value, but x minus 2 without the absolute value. What's the slope of the line? 1, okay. Now when the absolute value takes effect, it makes that, it doesn't change the fact that the slope here is still 1, right? So what about as x gets closer? If x is a little closer, what's the slope between those two? 1. And what if x is a little closer? What's the slope between those two? Still 1. So you're saying it's 1 as x gets closer and closer to 2, that slope is always 1, all right? Now, imagine though, if instead, if x is left of 2, in which case x is approaching 2 from below. If x is approaching 2 from below, what's the slope of this line? Negative 1. And as x gets closer, it's still negative 1, and so the limit is negative 1. Now, back to limit basics, if the one-sided limits are not equal, then the limit does not exist. Now, in this case, the limit represents the derivative, the slope, okay? It's what the slopes approach. So the slopes don't approach a single limit, don't approach one number, and because of that, then we don't know what to do with the derivative. Is the derivative 1 or is it negative? I don't know. And so in that case, then, the derivative does not exist. What the slopes approach is the derivative. And the slopes are approaching 2 totally different things, and because of that, the derivative's out the door. All right? Now then, if you were to look at what happened here, it was because there was just a sharp turn. The slopes went from 1 to negative 1, just like that. Any other point where the derivative does exist here, if you look at this point, the derivative wouldn't have a problem here because the slopes were negative, but they gradually get flatter and flatter and flatter and flatter before they turn positive, like over here. So there's a smooth transition of slopes. Here, there's no such smooth translation, whatever, of slopes. It goes straight from negative to positive, just like that, and the derivative doesn't know what to do with that sharp turn or abrupt change in slopes, okay? So this sharp turn is the first big reason why a derivative wouldn't exist. If a curve has a sharp corner or the old seagull function, the derivative doesn't exist at such a place because there's not what's called local linearity. It needs to be locally linear. If you zoom in enough, it needs to be smooth. Okay? It's pretty obvious, but I can't have a derivative at a place where the curve isn't continuous. If I had a jump in the curve, then the derivative can't exist at a discontinuity. And that could be a jump discontinuity or a hole. Remember all the different types of discontinuity. All of these violate the definition of the derivative in some way. You can't do the alternate definition here because f of c doesn't even exist. Okay? Or asymptotic. Surely that's also the case. Last but not least is a vertical tangent. If a curve does this kind of deal, like this, here the derivative does not exist. Now, the best way to explain why here is to use Leibniz notation. Remember, the derivative is the tangent slope, and slope is rise over run. Well, if it goes vertical, then it's rising without running. And if it rises without running, then what kind of denominator do you have? Yeah, right. So vertical tangents are cases where the derivative won't exist because the slope is, and therefore the derivative is undefined. So there are 3 cases of derivative doesn't exist. They are sharp turn, vertical tangent, and discontinuity. Okay? Those are things you're going to want to eventually commit to your noggin. All right. We'll practice that AP multiple choice questions in a second. All right. Now then, pretty common question is, all right, determine if this piecewise function is both A, continuous, and B, differentiable, showing appropriate justification. Now, if you were to, first of all, do continuity, then continuity would mean the limit as x approaches 1 from the left needs to equal the limit as x approaches 1 from the right needs to equal the point. When you approach from the left, which part of the function do you use? The top one, 2x squared plus 2. When you approach 1 from above, which function do you use? Bottom. And f at 1 needs to exist or be defined. In which case, we're looking at the inequalities. Do they tell you what to do when it equals 1? All right, so as x goes to 1, 2x squared plus 2 goes to 2 plus 2 or 4. As x goes to 1 from above, 4x goes to 4. And what about f at 1? Is f at 1 ever defined as far as what to do when x is 1? Yeah, it's the same as that right branch of 4. So f is continuous at x equal 1. Now that means that it has a chance for being differentiable. If it was not continuous, then it has no chance of being differentiable because you cannot have a derivative in a discontinuity. Because it is continuous, then I can go ahead and say, all right, what about the differentiable question? Right now, when you do differentiable, this is hard here, use the alternate definition to show. Now, this is tough, okay? You first of all have to know the alternate definition, and this does kind of happen on an AP free response every couple of years, so it's good to practice it. We'll have to practice it. So the idea is that the limit as x approaches 1, I'm going to write the alternate definition. There's the alternate definition of the derivative. That's the derivative at A using the the alternate definition, okay? So in this case, we're talking about as we get closer and closer to that point where those two meet, does the derivative exist? And does the derivative exist really as a question is it smooth there? Or is it some kind of case of whether the line and the parabola are just totally wacky different, right? That's really the question we're doing now visually. Do the slopes kind of smoothly match up? So let's start with this. F of x minus f of 1 over x minus 1. Now, I know that the two curves are meeting. Actually, I'm going to draw a picture here. I know that the two curves are meeting at 1, 4. The parabola is meeting the line. Cool? The question is it a smooth meeting or an abrupt change of slope kind of meeting? Now, you have to say, all right, if I look at what the curve does on the left side, which is to say when x is just a little less than 1, does that match the slopes between points on the right side? Please ask questions if you are not with me. So here, when x is close to 1 from the left, what's f of x? Which f of x do I use? Do I use 2x squared plus 2 or 4x? 2x squared plus 2. So the limit as x goes to 1 of 2x squared plus 2 minus, what is f at 1? We found it over here. F at 1 is 4 over x minus 1. Now I need to work that out. Right now, you'll see if you were to plug in, it's 0 over 0. So what should I do if I get a limit that's 0 over 0? Say again? Yeah, let's try and do a little canceling. If I take 2x squared minus 2, I could take a 2 out, and it would factor. I'm running out of room, so I did that all in one. I took 2x squared minus 2, took out a 2, and factored x squared minus 1. That's how I got here. Are you cool with that? All right, at that point then, you divide out of x minus 1, and you can find the slope. What's the derivative, or the slope, or the limit? It is? Hello? 4. It is 4, okay? Now, just so we're clear, x squared plus 2. I know this is kind of abstract. I can only imagine how lost I was when I was first learning this. But what we just did there, I know this is all a bunch of symbol pushing, but we took the point at 1 and with another point over here and looked at if you draw the slopes between those two and what happens as the points get closer and closer and closer together, what does that slope approach? And as that point went closer and closer and closer together towards 1, that slope started to approach 4. All right, yes? That makes no sense?
Yeah, well, I don't think, when you factor it, isn't it x plus 2 and x minus 1? Because if you take the 2 out, it's x squared plus x minus 2.
Oh, maybe I should have been slower. I have 2x squared minus 2, and I took a 2 out of both.
Wait, oh, I messed up, never mind.
Is it okay?
Yeah,
it's
I
entirely
messed up.
possible I screwed up, but so are we cool?
Yeah.
Okay, so we get 4 there, right? Now again, that's what, if I take points on the parabola with 1 and draw the slope, draw the slope, draw the slopes start to approach 4 on the left-hand side, right? Are you with me?
Yes.
Okay, now if I look at the line side, I kind of already know that the line has a slope of 4. So it feels like I'm going to see that it's going to work out, but I'm going to show the work because they are awfully picky on the AP test. So if I am using x's on the right side of 1, then which function do I use? The parabola or the line? The line. So instead of f of x, now I'm going to replace it with 4x. F at 1 is still 4 over x minus 1. Now, that I can factor out 4, dump an x minus 1, and that limit approaches 4. Now, what we just proved then is that the slopes from the left approach 4, closer and closer to 4. The slopes from the right are 4, so there really can't be some kind of sharp turn there. It's a smooth transition of slope of 4 into slope of 4. And therefore, because these two are equal, f is differentiable at x equals 1. Or the derivative exists there because the slopes match on each side. Now the good news is, the bad news is you might have to do that in previous one. And you'll need to. The good news is this is more often a multiple choice question, in which case you can cut a little corner or two. So check this out. On a multiple choice question, the problem might look something like this. F is the function defined by this craziness. Mx squared minus 2 for x less than 1 and k root x if k is greater than 1. If f is differentiable, what are the values of k and m? You've got this parabola meeting a square root function at 1, and it would have to be pretty doggone perfect, it would have to be pretty doggone perfect, first of all, for them to meet at 1, and second of all, for their slopes to be smooth at 1. You're trying to make a perfect m and k, so there's this smooth handoff between the two functions at some point. So that's the goal, right? Let's start with, if it's differentiable, it can't be differentiable unless it's continuous. Hi. Hey. So that would mean that the limit as x goes to 1 from the left, which uses mx squared minus 2, must equal the limit as x goes to 1 from the right, which uses k root x. For them to meet at all, that has to be true. What they approach from the left of 1 must match what the y values approach from the right of 1. At 1, what does mx squared minus 2 equal? Now you can't know m. So 1 is going in for x. What do you get? M minus 2, okay? On the right-hand side, we don't know k yet, but I know x approaches 1, so that approaches k, all right? So for them just to meet, m minus 2 needs to equal k. Now, if it's differentiable, then their derivatives at 1 must be equal. Let's say that as what the derivative of the function as x approaches 1 from the left needs to equal the derivative as x approaches 1 from the right. The slopes must match at 1, which is to say the derivatives must match at 1. Now you might say, well, don't you have to do this alternate definition stuff? And the answer is no. Only if you had to prove, or it says show justification, then yes, alternate definition is all that work. But if it's just a find m, find k, or multiple choice question, then gosh, you can start to use a little bit of derivative rules. What's the derivative of f when I'm looking at x is less than 1? So that's x is less than 1. What's the derivative of that? 2x, right? And that needs to equal the derivative from the right of 1. From the right of 1 is here. What's the derivative of that function? K over, k is a constant, so what's the derivative on root x? Or x to the 1/2. 1/2 x to the negative 1/2. Are you with me? Okay. The functions must equal at 1. The derivatives must equal at 1 for it to be continuous and differentiable. At 1, what is the left side slope approach or equal? 2. At 1, what is the right side slope approach or equal? K over 2. All right. Now with these two facts that need to be met, we can find m and k. K surely has to be 4. And if k is 4, then m must be 6.
Why is it set m on the left side for the derivative?
Why isn't there a 2m here?
Yeah, why isn't it 2x?
Thank you. There's supposed to be. Darn it. Sorry. Feel free to shout out those issues instead of mumbling to your friend. Is Rickman an idiot? Instead, let's bring them up as a whole so we can get through this stuff quicker. You're right. This derivative should not be 2x. It should be what? 2mx. Awesome. Thanks. So, at 1, what is this derivative equal to? 2m. And at 1, what is this derivative equal to? K over 2. So we have a little more work to do now. K is 4m. If k is 4m, then m minus 2 is 4m. So negative 2 is 3m, and therefore m is negative 2/3. If m is negative 2/3, then k is 4 times negative 2/3, or negative 8/3. Sorry about that, I made a mistake. All right. So, in a case like this where it doesn't say justify or use the definition of the derivative, then I could just say the functions need to meet, the derivatives need to meet. Cool? Okay. Let's talk about this. This is an AP problem from, I don't know when, 2003, I believe, but they're pretty common in every test. All right, so f is this piecewise function above. Which of the following statements must be true? First of all, how would you answer the limit as x goes to 1? Does it exist? Here, now keep in mind, this is multiple choice, so I'm not looking at your work at all. The question is just, can you get the answer? So, if the limit exists, then the limit from the left and the limit from the right must be equal. What's the left equal? At 1. Negative 1. The right, what does it equal? At 1. Negative 1. So does the limit exist? Yeah. So that's true. Okay? F is continuous at 1. How is continuity different than just the plain old limit? What's the extra condition? For continuity, the left has to meet the right, and the point has to be the same. So, the left and the right, we know they meet. Does that equal the point itself? Does that also equal, does the limit equal f at 1? Yeah, it does. At f1, it's using this function, and we already know that's negative 1, so that's true. F is both continuous and the limit exists. Differentiable, that means do the derivatives equal at x equal 1. So the first function, what's its derivative? Anyway, negative 2. Okay? What about the second one? What's the derivative? Negative 2x at 1, negative 2. So is that true? It is true. And so those are all true. The answer is B. All right. That's differentiability. Remind me again, what are the 3 reasons a derivative doesn't exist? Third, discontinuity or jump of some sort, and vertical tangent. Okay. Definition of critical number is a value of x in the domain. All right, critical numbers are huge, and this is actually the meat of set 36, but it'll just take a second. A critical number is a value of x in the domain, would you underline in the domain, of an equation where the derivative equals 0 or does not exist. Why would we want to find these? Well, imagine a derivative doesn't exist. One reason would be a sharp turn, right? In this case, f prime d and e, and we have it's a max there. Sometimes the derivative is 0, and that's a max. Sometimes the derivative is 0, and that's a min. And so the point is, critical numbers might indicate extrema. They're good places where you might be getting an error max, and that's why they're critical numbers. They're important. That is to say, however, that a function can be increasing, go flat, and then go back up to increasing. Now here, this is a critical number because the derivative does go flat there, but in this case, not an extrema. So critical numbers are places where something interesting might be happening, but doesn't guarantee happen. It's just a place to start looking, all right? So if I say find the critical numbers of x squared natural log of x, let's start by having in mind the domain. It says critical numbers are numbers in the domain where the derivative doesn't exist or is 0. So start by knowing the domain. What's the domain? X must be x is greater than 0. You cannot take the log of a negative. You cannot take the log of a 0. I don't have absolute value in this case, so there's no negatives allowed. All right, so good deal. Now, I take the derivative. What is the derivative? X squared times what? 1 over x, 4 plus 2x log of x. We have to use the product rule there, right? Okay. So, with a little cleanup, then you're going to set that equal to 0 undefined and solve. So this is x plus 2x log of x equals 0 or undefined. Are you with me? Okay? How do you want to solve that? This will require some algebra skills on your part. Factor out an x. If I factor out an x, I have 1 plus 2 natural log of x equals 0 or undefined. I want to find whether it's a 0 or undefined because either one's a good critical number. would you agree that this equation would equal 0 if x equals 0, but that is not in the domain, and so that would not be a critical number. What about 1 plus 2 natural log of x equals 0? If I solve that for x, what's the algebra I do? Subtract 1, divide by 2, then e it, or exponentiate it. So x is e to the 1 half or positive, negative 1 half or positive 1 half? Negative 1 half. Is that a negative number or a positive number? Positive number. That's equivalent to 1 over the square root of e, yeah? All right, so is that in the domain? It is. That's a critical number. Okay? That's your answer then, wherever the derivative doesn't exist or is 0, critical number. Try one on your own, please. The meeting's a little spotty. I hope you guys are really good at doing it. The algebra's the hard part. Usually people get the derivative right with the algebra. How are we doing? How many critical numbers do you have? 3? Right? Okay, so the domain is x can be anything that doesn't make a negative in the root. So x has to be small. Okay? If x is too big, subtracting a big number would be negative. So x has to be between negative 3 and 3. Are we good there? Inclusive. Inclusive. All right. The derivative, do you agree with the cleaned up chain rule that 2's divide out? And so you get negative x over root 9 minus x squared. Now when you get a fraction, which will happen a lot, you should break it into two cases. The derivative will be 0 if the top is 0. And the top would be 0 at x equal 0. The derivative will be undefined if the denominator is 0. And the denominator is 0 at x equal 3 and negative 3. Are those all in the domain? Are all those in that set? Yeah, they are. Okay, and so those are your 3 critical numbers. What's the graph of that look like? Just run it in. The original function is a semicircle, top half. And hey, is there anything interesting? Is there anything interesting about negative 3, 3, and 0? Well, yeah, those are mins and amounts. Those are important. Okay. All right. Notice also that at negative 3 and 3, those are vertical tangents. That's why the derivative doesn't exist there, because the tangent line goes vertical there. Undefined place. All right. Done. Questions on set 35. 35. 35. How did last night's homework go? Worked pretty well? 1 and 9. If you're missing like, between 0 and 7-ish a night without help, okay, if you're missing like 15 nights, well, you should be getting help. You said 1 and 9, yes, Tyler? Okay. What else? 24. 12. Okay. 1. Surface area of a rectangular solid. Did you use XYZ or length of pipe? Okay.
You find the
Surface area.
tangent. So you find that since it's slope.
Oh, yeah,
Y
because
prime is you plug in the calculator and do
the length and width are equal.
derivative of this.
So the length and width, did you use both L or both W? Both L? Okay, sounds good. What is the volume in terms of alcohol? All right, so volume of this would normally be length times width times height, but we're subbing in here. Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Okay, so now the question eventually gets to how you approach it.
University is known for its famous alumni, the director of Dr. Dre. They only use real cadavers on campus and are situated 30 minutes north of School. Viola is located in Colorado, California. They will be counseling for the 7th hour tonight at the house.
Plus 4L times the height. You can solve this for 8. So if you take 100 minus 2L squared divided by 4L, that.
If you have not turned in your academic and behavioral contract, please bring them to the office as soon as possible. Come check with the main office in Yorkshire.
So that's it. And then you want to evaluate it after and then you have to go to
Junior high students, tomorrow, Wednesday, September 26th, 7th graders with last name A through L will report to the cafeteria for 7th hour to meet with Mrs. McRae to complete a needs assessment survey. On Thursday, 7th graders with last name M through G.
So the tangent line, they give you the point already. So we're cool there. The slope, we need the derivative. That's going to require that implicit because y is unsolvable, right? So if I take derivative on that, it's the derivative of the outside times derivative of the inside. Derivative of x squared is negative 2x, and the derivative of y, don't forget, is 0. That would mean that dy dx is 2x over 2y, or x over y. So the derivative then, at that point, at 0, 1, is 0 over 1, and therefore the tangent line has a slope of 0. If I use that slope in that point, then it's y minus 1 equals 0, x minus 0, and so in essence then it's y equals 1, which is to say it's a horizontal line. This is a hyperbola, and the tangent line is okay? All right, 24, question on 24.
at that point.
It's a replacement.
Oh, shoot.
10 years from now, I'm not going to be talking about
Okay, so vertical tangents. A vertical tangent is when there is rise but no run. And so you need to first find dy dx, which is what gives you the tangent slope at all, and find what makes the derivative 0 in the denominator. That's what makes a vertical tangent if there's rise but no run. So let's start with the derivative. 1/4 is a coefficient. What's the derivative of x squared? X. 1/9 is a coefficient. What's the derivative of y with respect to x? 2y dy dx. Awesome. Equals derivative of 1 is 0. Cool? Okay, so if I solve for dy dx, I would subtract this over, and so it's something like negative x over 2 if I reduce first, right? If I divide this over, then I'm dividing by 2y over 9. Are you with me? Okay. Now surely that could be cleaned up, and I think it would probably be worth cleaning up, so I'm going to call it negative x over 2 times reciprocal 9 over 2y. Tracking? So negative 9x over 4y. Are you with me? Okay, now this is undefined if the denominator is 0. And so that implies y must be 0. If y is 0, then x is plus or minus 2. So the places where the graph goes vertical are 2, 0, and negative 2. It's not just enough to find the y, you're going to have to find the x that goes with those. Now, if you think about that graphically, it would make sense. This is an ellipse like that, and it's vertical like that. Okay.
No, actually, so
Vertical. Exactly. So I feel like that's
I really want to get out of this.
if they want there's a curve. So once I have the y, and then
Who cares? It's just for Thanksgiving tomorrow.
have a good day, folks. Hi, Jesse. How are you?